Look at the sheer volume of movement here in the meadow at dusk. Every single creature you see carries its own set of measurable facts. If you're the magpie clerk assigned to take the census, recording those facts presents a logistical nightmare. You need to log 2 distinct, connected measurements for every individual animal, like a squirrel's autumn acorn count and its winter weight. Writing those pairs down in endless, unreadable ledger columns won't help you understand the population. You have to translate those paired numbers into physical space. We map them visually because the human eye is remarkably good at spotting hidden relationships in shapes and terrible at finding them in raw tables of data. The horizontal axis tracks acorns cached, and the vertical tracks winter weight. Taking one specific individual, we plot its data moving 40 units across and 12 units up. That single dot represents exactly one creature. It is not an average nor 2 separate animals. That is the core logic of bivariate data. The dot's entire mathematical job is to permanently lock 2 variables together so they cannot be evaluated apart from one another. Now look at this chart of 40 individual dots. Step back and a macro pattern emerges. The dots form a climbing cloud from lower left to upper right. We call this a positive association. An increase in one variable corresponds directly with an increase in the other. In real-world terms, it tells us that squirrels who hoard more acorns tend to carry more winter weight. The cloud is fuzzy rather than a perfect straight line because natural biological variations exist. Squirrels are squirrels, yet the overarching predictive trend holds true. The second chart plots a rabbit burrow's depth on the horizontal axis against the severity of frost damage on the vertical. Here, the cloud falls. Deeper burrows pair with less damage, creating a downward trend. This inverse relationship is a negative association. Recognizing this shape gives the young rabbits the exact mathematical proof they need to justify the heavy labor of digging deeper burrows. Now, let's look at a third chart, plotting whisker length against the number of acorns cached. The points scatter randomly across the grid. There is no directional shape here at all, which indicates 0 or no association. Reading the slope of the cloud immediately answers whether 2 trades grow together, naturally trade off, or operate entirely independent of one another. If we return to our original acorn and weight chart, you'll notice a single data point sitting far outside the established climbing trend. This individual recorded a massive cache of 65 acorns, but paired it with a dangerously low winter weight of only 8 ounces. Mathematically, this anomaly is an outlier because it radically defies the expected shape of the surrounding cloud. There is a strong psychological temptation to simply erase a dot like this because it ruins a tidy visual pattern, but doing so destroys scientific accuracy. Instead, the clerk investigates and asks why. It turns out this dot represents an old squirrel who buried his large cache near a localized flooded oak tree where every single acorn spoiled. The mathematics of the chart weren't flawed. The anomaly simply captured a highly specific environmental event that the general biological trend missed. Look closely at the shapes. A rising cloud means positive association, a falling cloud means negative, and a shapeless scatter means none. One dot equals 2 inseparable facts, and the outliers that break the pattern demand rigorous investigation, not an eraser. This chart shows us exactly where this analysis goes next. Once you confirm the directional shape of a data cloud, you can lay a straight mathematical rail directly through its center and use it to predict the future.